Today we will start with our fourth class. So, in the last class, we were discussing some concept related to bias and variance. So, by this time, has anyone gone through this concept? Can you give me a brief overview of what you understand by bias or variance? Anyone?
Ma'am, these terms we come across related to underfitting and overfitting
Mm-hmm.
in some sessions in NPTEL.
Mm-hmm.
That where the for the underfitting the bias is high and variance is low, and for overfitting the variance is high and bias is low. But now the problem is we are not. I am not able to understand what is the term variance actually, and bias. We know that there is a bias is a tendency to train the model in certain way. That is the bias, and due to that, some error is added into the prediction. That is the all we know about it.
So, ma'am, in simple terms, what I could understand from bias is like when you are expecting some answer from a machine learning algorithm or like a model,
Right.
it is not giving you the expected result in terms of like, say, if you're expecting him to give a positive result, it's giving more negative. So expected result is not coming out of it. But I second with Sandeep sir saying that how variance is different. Variance and bias are like little confusing. One fits in, one comes with like underfitting, another comes up with overfitting like of scenarios. That's what we could understand. So probably you will have to help us.
Okay, so when you say overfitting or underfitting, so what do
Yeah.
you understand by these two terms? When you
Okay.
say underfitting, what do you understand by underfitting? What happens
Um,
actually? If we
sure.
don't go by the technical terms,
Sure.
just by your meager understanding.
Okay. So what I understood from underfitting is like when like regression line, for example, if we are talking about, it is not like it's like something where like you have less number of data and you are trying to fit everything with from that less number of data. So your line might be kind of like going just in the center, not considering all aspects of the positions. So anything like which is just drawn with less number of data and its accurate position is not clear. Overfitting is you're trying to get into each and every variable so closely and you're trying to build a kind of a line which is meeting all those variables.
In the layman term, ma'am, Soumya ma'am, actually underfitting is what the model is not able to give the correct prediction on training data itself. So the training data is not sufficient enough to train the model, and in that case. It is ignoring the input data set, and it is directly giving you the output, predicting the output, which is incorrect. And in overfitting case, we are training our model with so many features that it is detecting every test input as a true positive, like this.
Right. Somewhat, yes. This understanding is correct, but then you have to be careful with the terms you are associating with. Bias is associated with the error of the training data, whereas variance is the term associated with the error of the testing data. There is this slight difference that you need to identify. So essentially, in layman terms, if we have to say, then bias is associated with your training set while your variance is associated with your testing set. And this we will understand with a brief example so that you can correlate it with the concept of overfitting and underfitting. See, if you remember my class, somebody asked the concept of overfitting or underfitting. So, when you talk of underfitting or overfitting, it is a comparison between models, not a particular model. When you are being specific that it is linear regression, then you are very much, ensuring that the equation of that line of that function will be of the form y equal to mx plus c, right? So when we are discussing linear regression, then the concept of overfitting or underfitting cannot arise because we have fixed or earmarked that this is the function that we are dealing with. The concept of overfitting or underfitting will arise when you are discussing the variation between models, whether it is a logarithmic curve whether it is an exponential function, or whether it is a polynomial function, or whether it is a straight line function. When you're comparing different functions, then only the concept of overfitting or underfitting can arise. When you are talking explicitly of linear regression, then you are being specific that you are talking only what is the best fit straight line that you can draw. There no other question of any other model arises. So no question of overfitting or underfitting can arise when you are being specific about the model. When you are comparing amongst different models for the same set of data, only then the concept of overfitting or underfitting can arise. I hope I'm clear.
Okay, ma'am.
Okay, so now let us consider that in this instance that I'm showing on screen, you have a data of say height and weight of a person. Okay, so you
Excuse
have,
me, ma'am.
yes.
I want to know in the assignment question there has given when there is a complex data or short data, even then overfit occur.
Hmm.
So please explain it. Even then there is a short and complex data. How can overfit occur in the model?
Okay, so I think you will be able to answer this question once you go through this concept of bias and variance. You will yourself be able to answer this question. So, on
Okay,
the
ma'am.
basis of data, you will be, in fact, I will ask this question at the end of this explanation. So, let us see if you can recollect the concepts nicely or not. Okay, so shall I go ahead with this example first?
Yes.
Okay, so let us consider, for example, we have a data of height and weight of different people. Okay, so as your weight increases, your height also increases for the person you observe, and there is a certain scenario wherein, after which your height ceases to increase much, even though there is a lot of, increase in weight. So these people here are kind of obese. So with respect to their height, weight is slightly on the higher side. Okay, and here you get a proportionate increase, and here you get a disproportionate increase. So let us assume that for the sake of simplicity, we have this kind of data for now. So what is the evident trend that you can see here? Somewhat like this, right? If you try to draw a moving average, something like this, right? This is the kind of curve that you can see visibly from eye approximation, right? So it is imminently, definitely not a linear regression problem. This much you can read from the data set just by your eye inspection, right? This does not look like a linear fit, does it?
Okay. No.
Not really. But you are also not aware whether or not it will be a 2-degree polynomial or 3-degree polynomial, or what kind of curve it will be, right? So let us, randomly pick and choose some data from this as the training set, and some data from this let us keep it later for a testing set. Okay, so these blue data sets, let us assume that we will train our model on these blue data sets. Okay, so far clear?
Yes, ma'am.
Okay, so if that is the case, then we isolate these data points and we keep the remaining data points for our testing, how well our model is trained. Let us assume that, for example, if we draw a straight line, something like this, on this training data set. So, what is the kind of error that you get? Is
This
it
is a
high?
residual error. Huh?
You get a high amount of error. Okay, now let us assume a case wherein you have a squiggly line which passes through each and every individual data set. So if you basically calculate the error in this case, you will get zero error, because essentially all your predicted values are overlapping with your labeled values, actual values, right? See, this is the point, and your line is also passing through this. So predicted value and actual value are coinciding. So in this case, the error is zero. Similarly, here also error is zero. Here also error is zero. Here also zero. Here zero, zero, zero. So essentially, if you sum it all up, you get a net zero error for this red squiggly line. See, I'm not talking of this moving average, this line. Just ignore this line for the time being. Just focus on the red line. If we see, then there is absolutely zero error. that this line is showing, because it is passing through all of the data points. Whereas in this case, in the case of the straight line, it is hardly passing through any of the points, maybe one or two, and basically there is a huge amount of error that is associated with it, right?
Right.
Okay. Now, why I'm saying that this is underfit and why I'm saying this is overfit will be clear if you look. See, this was the error associated with this line, whereas this line had zero error. So basically, there are no such dotted lines associated with this case, second case. Whereas the sum of all these dotted lines, the distance, if you sum it all up, it is the net error associated with this line, right? Now, if you include your testing set here, and if you test it, you will see that the error which you designated in the case of straight line remains almost similar. If you add these all up, then the error is more or less similar to the previous case with your training data set. Whereas in the case of your testing data in the second case, there is a tremendous increase in the amount of error. Do you see the difference?
Yes, ma'am.
When you were training on a specific data set, there was a certain error associated with the first case, and there was zero error associated with the second case. Whereas when you started testing these two models, for the first model, the error remained more or less constant or similar, whereas the second case, it drastically increased from zero to a positive value of error. There is a net error associated with it now. Do you follow? Do you follow the
So what is,
difference?
yes, still.
Definitely, this is the case of overfitting. This is for sure. In overfitting, what happens is, even though your training data set shows a net amount of zero error, when you test it, there is a net amount of positive, significant increase in your error. That only happens when your model is overfit. In case of overfitting, there is no constancy that you can observe in your error associated with your training set as well as your testing set. Now, coming to the first case, if your model had been well trained, then essentially the net error, even though it is constant, it should be a low magnitude value. It should be a global minima. Essentially, when you discuss the loss function or cost function, you will see that there is a concept of weights and bias, right? So when that happens, essentially you try to optimize your function, your cost function, such that the net error associated with that model is the minimum that you can get. When that happens, only then your model is optimally trained. Otherwise, even though you are obtaining a constant amount of error in both training as well as testing phases, you will still not have a good fit. See, in this case, there is a constancy, but the fitting is not good, right? So that is the case of underfitting. You still need to move ahead with the fitting. And here, this is overfitting. You have fitted it more than the optimal value. Do you understand the difference between underfit and overfit?
Whatever you discussed so far, it is we understood. But tell us the difference in terms of bias and variance now. How bias is high and how low, variance is low in first case, and how bias is low and variance is high in second case.
Okay. So, in the case of underfitting, which is our this case, first case, in that case, your bias and variance both are high, while the bias, although it is low in case of overfitting, the variance is literally very, very high. See, variance essentially deals with the testing set, whereas bias deals with the training set. So, in case of training, if you see, then there was an error associated with the first one, whereas there was almost zero error associated with the second one. So, the bias was high in case of the first case, whereas bias was low in the second case. So far, followed me?
Yes, ma'am.
But
In
when
terms
you
of
come,
training set,
see, this
this
is
is
your
true. This
this
is
is
true
your
for training set.
training set. The blue ones are your training set, and there is error associated, there is high error associated with your training set in the first case, so the bias is high, whereas there is almost zero error associated with your training phase in the second case. So your bias is low. Now let us come to variance. The testing phase. The variance in the case of first case is still high, whereas in the second case also it has become high now. So the variance is high in both the cases, overfitting as well as underfitting, which is associated with your testing set. But bias in the case of underfitting is high, but in the case of overfitting, bias is low. Do you follow me so far?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Is there any doubt, any confusion what is bias associated with and what is variance associated with?
So far, so good, ma'am.
Okay. So if you're following me so far, so ultimate aim is to optimally train your data, neither to underfit nor to overfit. So we will come from the stage of underfitting to the stage of good fitting, not overfitting. So we have to start from the straight line and we have to try and fit it into other such functions and see whether or not there is improvement in the total cost function that we obtain. So essentially we want to lower the bias as well as lower the variance. Okay. So before I discuss this, I will go on to, yes, this slide. See, when you are talking of low bias, so essentially you are talking of how precisely you are hitting the bullseye. See, this is a bullseye. So essentially, you have to earmark your center. You have to hit your center. How close to the center this is. That is called bias. But when you're talking of variance, it talks of how sparsely or how closely related your observations or your data is or your predictions are, right? So when you're talking of low bias, then that means you are moving closer to your bullseye. When you're talking of low variance, that means the points amongst themselves are closer to each other. These are not the same thing. The points may be closer to each other, still not be close to the central or actual value. Then that is called low variance but high bias, because it is not close to the central value, so it is high bias, but at the same time they are close by amongst each other, so it is low variance. When the points are sparsely distributed, then it is called high variance. These two cases. But in the first case, if you see, then this is low bias, because although they are sparsely distributed, they are somewhere around the actual real value, whereas in this case that is not the scenario. So do you understand the difference between low bias and low variance, or high bias and high variance?
In this case, for such a scenario, it is clear. But how we will relate to our ML concept,
Yes.
ML understanding.
So when we talk of ML, you must have heard that the quality of data is of utmost importance. How well your trained model is, that imminently includes that you are assuming that you have good quality data. When do you say you have good quality or reliable data?
The data is clean and there is no missing values and outliers.
Yeah, not no missing values or outliers, but it is representative of the whole set. You must have gone through the concept of sampling. See, when you take a survey, do you take a vote from each and every individual in the whole population? You don't, right? What do? You do sampling. You pick and choose certain set of individuals who will be from all the communities that are concerned, so that you have a representation of the whole population, and from that sample essentially you do the training, or you
Right.
do the analysis. So that is essentially what is required when you are choosing. See, in this case, if you focus on the blue and green points, you will see that I have picked and choose those points which were representative of the whole population. It should not be that I have chosen just, a set from this side and I've ignored altogether here. So all of these are blue and all of these are green. In that case, my training will be flawed. Why will it be flawed? Because my training set is not representative of the whole population of the point that I have. But if I randomly do this, then yes, it is representative of the whole population of my data that I have. Only then I can say that my data is reliable. If your training set are and testing set are altogether isolated, then your training is also not proper and your model is also not fit properly. So you understand the concept of sampling, right?
Yeah, ma'am, correct.
We know the sampling, random sampling.
Yes.
So, in terms of bias and variance, how you will say that it is how the what is variance means? It is can I say that variance is a spread of the data and bias is the error introduced in the prediction?
Not essentially. It is the error associated with the spread of your data. You're testing your data with a certain set of values, which is not coinciding with your training data set, and it is still showing the same amount of error that was the case with your training set. Then it is essentially not because of a flaw in your model, it is because of your data set. So in that case, you can say that the variance is low. See, I will try to illustrate this with another. Yeah, this is your model complexity, right? And by model complexity, let us assume for now that it is the degree of your polynomial. So if it was linear, then it is somewhere here. If it is 2 degree, it is somewhere here. It is 3 degree, it is somewhere here, and so on and so forth. Your degree of polynomial is increasing. Okay, and this is your error which you are plotting. So when I say error, I am referring to the whole cost function altogether. Okay, so if that is the case, then when I say that it is the case of underfitting, so what is the condition for underfitting? That your bias should be
Bias
I.
high and your variance should be
low.
really.
No, high.
No, no.
For underfitting, bias is high.
High.
So your underfitting case, essentially your bias is also high and your variance is also high,
Also, correct.
right? So which is that case? Does this curve
Underfit.
represent that? Is your error going on increasing?
Decreasing actually.
It is decreasing. As your model complexity is increasing, it is decreasing. The error is decreasing. So that is definitely not the case with underfitting. Now let us look at this case. What is the case? Here, your error is high. Here also error is high. So whether your model complexity is less or high, in both the scenarios, your error is high. But there is an optimal situation where your error is minimal possible. I would not say low, but this is the least possible. And this is exactly that minima that we are referring to as best fit, where your cost function is the minimum value that it can assume for any given model. And that particular degree, if you pinpoint, so that is the exact degree of your polynomial or your model that should give you the best fit of your data set. Besides that, if you go to a lower degree or a higher degree of the model, in both the cases, you will see that the error is increasing.
What is this division, ma'am? And it is
This
left
division
side
is not for
underfitting.
underfitting and overfitting. I think just understand that in the case of underfitting, this is the curve that you get. And moving from underfitting to this is the best fit. If you go ahead in this direction, this is again underfitting. Whereas in this scenario, if you discuss, then this is the case of overfitting. In overfitting, what happens? Bias is
Low.
Low.
and
Low
variance
bias
is.
and high.
High.
So there is this inverse proportionality that you get by a hyperbolic kind of trend. Do you follow me so far?
Yes, ma'am.
How will I will explain this concept to my under bias and variance in terms of this.
See, this is the best example that you can give. In terms of bias and variance, if you have to talk of bias, you talk of the training data and you show the illustration, this difference between the errors associated with your training data. You see that in the case of first model, which is a linear model, you get a specific high amount of error associated with it, which is high bias. high error associated with your training set is high bias. Whereas,
And bias.
Mhm.
Bias is also mean as restriction now.
Restriction as in?
No, Soumya, she mean to say that the bias means the certain way to handle the things only. Means so we are handling certain things in a particular using some particular tendency. That is, she is meant to say.
Yes, there will be a certain tendency associated with it. See, there was a
Ma'am, I
question.
mean to
Yes, please.
actually I mean to say that bias is also mean as restriction that we kept on model.
If you go by the literary definition of bias, then yes, that is true. But in this case, bias is referring to that your model is specific to only the training set. The moment you change your data set, or you put in the testing data set in this phase, your model suddenly becomes invalid or not so accurate. So that means your model was very much particular to the chosen data set on which it was trained. It was not universal for the entire data set. So that is the kind of, I would say, association that you can do of the literary meaning of bias and the bias associated with your machine learning algorithm. Do you follow me so far?
Yes, ma'am.
Yes, ma'am.
There was this question one student asked related to your data set, which I said that I will be explaining at the end of this explanation.
Actually I was asking
Mm-hmm.
there is a if there is a short and complex data, even then overfit is occur.
Right.
That was the question given in the assignment. So please can you explain it?
Okay, so by this concept and understanding, do you can you correlate this? Would you like to give it a try? Now that you understand how important the quality and sampling of your data is, so in the case when you have less amount of data, in that case overfitting is the most probable scenario. So can you correlate that?
Ma'am, I think quality of the data has not provided. So
Mhm. When it is saying that your data is sparse, data is less. So when your data is less and it is more complex, that means that it is not representative of the whole sample or whole population that you are referring to, right? When you
yes,
say
ma'am.
complex data, that means it is not including certain set of data. It is only including a peculiar variety of data. So it is not covering all the set. And you're also saying that your data set is short or less. What happens in that case? You try to fit it with all of the data, and it is actually unreliable because when you actually use some other set of data or a more reliable set of data, then the most probable scenario is that because of your unreliable data, you've tried to fit it, and in that process, although you reduced your bias, your variance is very high. The moment you use some other set of data which is less complex, increases the value of your error. Now the moment your testing set shows a high amount of error, although the amount of error was less in the case of training phase, that is the scenario only in the case of overfitting. Whereas if you use a representative data, in that case, overfitting is not the most probable scenario. The model is trained to take into account all of the related kinds of data points. So, in that case, the same model, when it is used for some other data set, then also it will be equally valid. But when your data set is short or not representative, in that case, your data set is not reliable. Suppose this is my data set, these 3 points are my data set. So I can very well assume a model something which fits through these three data sets. Now, the moment I have these four data taken into account, now suddenly this model becomes invalid. So that is the case when it happens in the case of overfitting. Do you realize?
Yes, ma'am.
So is there
Fitting is
any?
invalid, or ma'am, or can I say overfitting is on test data the model becomes invalid, right?
Exactly. The model becomes, I would not say just invalid, I would say less precise. That would be a better term to say.
Okay, ma'am.
Yep. Now let us come to this concept. Yeah. How about this? In this case, your training set as well as testing set shows the similar amount of error, as was the case in the straight line. Your training set as well as testing set showed the same amount of error. But when you compare the overall error value in the case of straight line compared to the case of this parabolic curve, you find that the overall error is lesser in magnitude as compared to the straight line. So, which is a better fit in that case? If you have
Where
to
the errors
compare,
are less.
sorry,
Where the errors are less.
see, I'm here firstly comparing the training and testing phases of this parabolic curve that I have. Okay, and I'm seeing a similarity in both the scenarios, the training as well as testing phases. And I've also noted the magnitude of the error associated with these. Since they are similar, so I can note down just one value. Now I am saying assume the case of straight line. Here also, in the training and testing phases, the overall value of your errors associated with these two cases, as well training as well as testing, the overall magnitude is similar, but the magnitude is higher as compared to the parabolic case. Although it is similar when compared amongst the training and testing sets, when compared amongst each other, I'm seeing that the magnitude of error is higher in the case of straight line when I compare the parabolic part. So which model is a better model, the parabola or the straight line?
I think
Parabola.
parabola.
Exactly. So that is what I'm trying to say. That the concept of bias and variance arises when you are comparing the testing and training sets. This is the training set, this is the testing set. But if you have to compare two different models, in that case, you are comparing the overall cost function or the net error associated with that model. Okay, so that is the fundamental difference. So even if your straight line shows a similarity amongst the training and testing sets, the overall value of the error associated with is higher than compared to the parabola. So I would say that the parabola is a better fitting model on this data set as compared to the straight line. So do you
Got it.
understand that?
Yeah, perfect.
Okay. So always revise this slide. This will further, enhance your understanding of what is bias and what is variance. When I
One
say
request is there.
yes,
Can you please explain parabola and straight line
okay.
once more?
Okay.
Ma'am,
Suppose.
can I try quickly for
Yes,
this?
please. Yes, please.
Okay. So straight, if you try to create a straight line and the errors that you are getting is say 1.1 on say, a straight line, always 1.1. When you are using the training data, all the errors are like of magnitude 1.1. When you run it on the testing data, you again get the errors on 1.1. Okay. Now, if you use the parabola, you get an error of 0.75 on the test training data and on the test data also. So, which one will you prefer, parabola or
Parabola.
the straight line?
Yeah, parabola. Thank you.
Right?
Okay. So now you understand what is called a good fit and what do you understand by bias and variance. I hope this part is very much clear.
Ma'am, we can proceed.
Okay. So if that is the case,
Yeah,
then
you can proceed, ma'am. Thanks.
yeah. So now moving on to the logistic regression. So we had in the previous class we had discussed what is logistic regression, and we had also discussed what are weights and bias associated with our model, right? So we had discussed this equation. If I just go back, so we had discussed this equation wherein this was similar to the form of the straight line. However, now these are not just real numbers, these are actually matrices that we are dealing with, wherein your x can be n dimensional feature vector, input feature vector, whereas w is nothing but your weights associated with those feature vectors. Vectors which features are more impacting your model or more affecting your outcome or output, and which features are less affecting your outcome or output. So that is how you will allocate the weights associated with those particular feature vectors. So this will be say n dimensional 1 by n dimensional matrix, whereas this will be m by n dimensional matrix. This is your overall understanding, overall representation of your model. So we will move forth from here to this. Okay, so I had in the former class also illustrated that how from simple regression based problem you are actually moving to a classification based problem, right? Can anyone give me a brief overview of how you do that? How do you do that conversion?
Ma'am, can I explain it?
Yes, please.
Here we are using a logic transformation
Mm-hmm.
and using some mathematical calculation. Actually, we are using Sigmoid function here to squeeze values of response between.
No, if you have to understand in simplistic terms, then
Okay, ma'am, I can.
Ma'am,
yes, please.
we can use probability.
Yes, you can use probability, but how?
Ma'am,
We can when we predict the values
Mm-hmm.
from the regression,
Mm-hmm.
and then we will convert it into a probability from 0 to 1,
Exactly.
in between from 0 to 1, and we can set according to the requirements the middle value, suppose 0.5, we will take it as 0.5, and the value of probability above 0.5 would be considered as yes, and below values can be considered as no. In this way
Exactly.
we can classify simple
Exactly.
regression.
Exactly.
So
So ultimately, when you are dealing with classification, particularly binary classification, then it is basically a yes and no kind of question, right? So either it is true or it is false. This is binary, right? So when you are dealing with a binary classification problem and you've got a regression expression, what you essentially do is you convert that expression into a form which would always give you a value between 0 to 1. It will not assume any other value than 0 to 1. So now any value ranging from 0 to 1 will be a probability distribution kind of function. And once you get the probability value, then any value greater than zero point 0.5 would mean yes, and any value less than zero point 0.5 would mean no or false, right? So this is how you move from a regression based problem to a classification based problem. So you've basically converted your expression to render a value between 0 to 1, and once you get a value from 0 to 1, you assume that from zero point 0.5 onwards, if it goes beyond that, then it is true, otherwise it is false. So you've now segregated these two classes, so it's become a binary classification problem. So if that is the scenario, then what is the kind of output that we get? We get the output in the form of, this is the representation that we do. So let us take a value y hat, and y hat is nothing but the probability that y is true or y is equal to 1, because y can assume a value from 0 to 1, right? So let us this y hat is the probability that y equals to 1, given that x is your input feature vector or matrix, and this matrix would take into account all of the variables, whether or not, even if it is a multivariable problem, then it will take into account all of the variables, and your model will take into account the w associated with it, that is the weight associated with that feature input vector. So if I would have represented, because I had this linear function, right, wx plus b, y equal to wx plus b, where w was your weight and b was your bias of your model. So if this is my expression, then definitely my y value has a range in all the real numbers. I cannot constrict it between 0 to 1, which was my demand in terms of probability. So this function which I had got for regression, I will simply take a sigmoid of that function. And what does sigmoidal function do basically? It converts your any real value to come in the range from 0 to 1. So now my y value will assume any value from 0 to 1 only, no other value. And how do you represent that sigmoidal function? Let us assume that we are talking of sigma of z. If z is your this horizontal axis and sigma z is your vertical axis, then I am talking of the function sigma z such that 1 by 1 plus e power minus z, where z is your horizontal axis, the values on your horizontal axis, right? So any real value, if I just extend this axis from minus infinity to plus infinity, any real value that I get, it will simply lie in the domain of 0 to 1. So I have now constricted my range. The moment I get any other value, it will take into account this sigmoidal function and it will give me a value in the range of 0 to 1. So far, so good?
Yeah, ma'am.
Okay, so now what is the speciality of this sigmoidal function? Now let us assume that your z is a very high value, positive value. It is plus infinity. In that case, what will happen to this? E power minus of infinity. What is this value?
It will approach to 0.
It will approach to 0. So what is the overall value of my function then? It will approach to
1.
1,
One.
right? So that is the maximum that you can get. Now let's talk of the minimum. What is the minimum value that you can have? It tends to, z tends to minus infinity. If that is the scenario, then e power minus of minus infinity, what will be that value?
Maximum.
It will
It
be
will
the
approach
highest
to
value.
infinity.
It is infinity. It tends to positive infinity.
Infinity.
So in that case, what is my function's value?
Zero.
It
One
tends to
upon infinity.
0.
1
1
by
upon
infinity is
infinity,
0.
it tends to 0,
Yeah.
right? So essentially, when I'm talking of the range of my z from minus infinity to plus infinity, then my domain of the function is coming in the range of 0 to 1. Proved it so far? How it is coming in terms of probability?
Yes.
Okay. Now, in this case, let us go ahead with the dimensions. So, if W is the weight associated with the input feature vector, so how many input feature vector do we have?
1.
Only one.
Here in this case, we have one. But in case of multivariable problem, how many can we have?
More than 1.
A number of features we will have.
N number of features that you can have. So whatever is the dimension of your x, if I have to count it this way, then if it is an m by n matrix, then I am talking of n number of columns, right? So as many number of those columns do I have, that many number of weights I have to give, right? So suppose if I take the instance that I had discussed in the previous class, then in order to estimate the price of the house, this is a regression question, but let us just stick to the example that we have because it is multivariable problem. So in order to estimate the price of the house, it depends on the variable that how many bedrooms are there in the house, how many floors are there in the house, how many years the house has been built on and so forth. So you can have n number of variables associated with it, and n number on those n number of variables will also have n number of weightage associated with it. So if the number of your input feature vectors is nx, which is the number of columns of your x feature vector, then what is the domain of your weight, the matrix size? It is any real value, but it is not just any real value, it is the whole matrix of those real values. And what is the size of that matrix? It is same as that of the number of columns in your x feature vector, that is nx. Followed me so far?
Yes.
Okay, so if I have an x input vector of the dimension m by n, where n is the number of those features vectors, that is the number of my columns, and m represents the number of my data points that I have. So if I've talked of, say, m data points, it doesn't define the size of my weight matrix. But if I have n features, then it does define my size of my weight matrix. Clear so far?
Yes, ma'am.
And when we talk of the bias, it is just a constant term. So it is just, its domain is just any real value. Simply you can assume this as maybe the base price of your house. So even if all the feature vectors, everything is zero, even then there will be some price associated with it. Those you can assume as the constant values. So that is the domain of your bias. So this is how you define the size of your matrices or size of your parameters. W and B are the parameters associated with your matrix, wherein your domain of W is any real number matrix of the size 1 cross nx, whereas the domain of your bias B belongs to any real value. That depends on the model. Okay, so now if that is clear, now let us come to the loss function. Now, what is loss function?
It is a single individual error that is nothing but a distance between the actual and prediction value.
Hmm. It is a function associated with your individual data set's error, right? So it is descriptive of the error associated with your data set, but just one particular data set, not the entire training set. When we are summing up the whole set of loss functions over the whole training set, then it is essentially the cost function, right? And we are to minimize the overall cost function, not the loss function. Loss function is just individual data sets error, not the whole. Okay, so if that is the case, then in this scenario wherein we are discussing supervised learning, so we have labeled data and it is a binary classification problem. So we've converted it from a regression based model to a classification binary classification problem, and we've defined the probability terms, and we've taken a sigmoidal function. And so we've got our values, our probabilistic values as y hat, and we've our labeled data set values as y. So here the error associated with it is y minus y hat, and we could simply take a square of that. But that error associated with it, do you think that this function will have just one minima? Assume that it is a multivariable problem. In that case, do you find that this will be a convex function wherein you will have just one global minima, or there can be n number of global minima?
Multi-picture, it is n number of global minima.
N number of global minima, right? So this is not a very reliable loss function that you can depend on. Although in this case you are having the positive outcome of, you are not algebraically summing up all the errors, so basically they are not cancelling out each other, because when you are squaring it you are essentially adding up all the positive values, so nullifying effect is not there. But still this is not a reliable loss function. Why? Because this function itself is causing an optimization problem, because you cannot optimize a function wherein you are not getting a global minima or maxima, right? If you require a global minima, in that case you should have one particular minima which is the lowest value of all. Only then you can talk of global minima. If you have multiple minima of similar ranges or similar values, in that case you do not have a global minima for the function. And if you do not have a global minima, you can get multiple types of models which give the same result. So if you have to define a loss function, then I will discuss in the subsequent classes of how we came about it. But let us look at this particular loss function. If this was our loss function, then what happens? Assume that your value of your labeled data y is 0. In that case, what will be the loss function? Since your y is 0, this first logarithmic term gone. Now you are left with this term where you are substituting y as 0. So essentially you are left with log of 1 minus y hat. Minus of log of 1 minus y hat is your loss function. And if you were to minimize your loss function, minus of log 1 minus y hat, if you have to minimize, then basically you have to maximize plus log of 1 minus y hat. So if you were to maximize plus log of 1 minus y hat, then you were to minimize y hat. And what is the minimal value of y hat that you can have?
Zero.
Exactly.
Sorry. Zero.
Y hat is a sigmoidal function, and the minimal value of sigmoidal function is 0. Now let us go ahead with the second example. Assume that your labeled data is the highest probability, that is 1. Then the loss function is rendered as, see, the second function, the second term 0. Why? Because when your y is 1, then this term is 0, and this multiplied by 0 vanishes this whole term. So you are left with this term only. So when your y is 1, your loss function is minus of log of y hat. And in order to minimize that, you have to maximize log of y hat. If you have to maximize plus log of y hat, you have to maximize y hat. And what is the maximum value of y hat?
1.
1. So basically, you've defined a loss function such that when your y is 0, your y hat is also 0. When your y is 1, your y hat is also 1. So you've not only restricted your probability value, you've also assured from this sigmoidal function that your values of y, which is labeled data, coincides with your predicted data when you are minimizing or maximizing.
Ma'am, why we are taking log here?
If you do not take the logarithmic function, then essentially the effect that you are getting here, you will not get it. I will discuss it in the subsequent lectures. For now, let us compare only these two functions. So provided the option, you would go ahead with a function which has the characteristics like this, wherein you can get a global minima. See, this is also one function. So if let us take for now that we are not having a multivariable problem. In this case, there is just one input feature vector. In that case, it is easier to imagine. If it was an n dimensional feature vector, in that case you would have a space of n plus 1 dimensional vector, and that is beyond human mind's capacity to perceive. So that is why the maximum, because we can only perceive up to 3 dimensions. So let us, for the sake of simplicity, assume that we've been talking of the space wherein your w is one axis, bias b is another axis, and number of your terms in w matrix is just 1. If this number of terms in w matrix was more than 1, then you would require more than one axis to define it, right? So this is your y hat, vertical axis, and you've got two horizontal axes as w and b. So basically the dimension of w and b is same, that is 1 dimension. So basically overall we have 3 dimensions, and in this overall 3 dimensions we can see that this has a global minima. This plane or surface or whatever you call it, it has one global minima. But in this case we are not having one global minima, we are having multiple global minima. From an approximation, I can see one here, one here, one here, one here, and one here. I can see 5, although there may be more, depending on what is the characteristic of your surface. So it is not a very, very reliable way to go ahead with your minimization of your loss function, because you will have multiple minima. But in order to minimize your loss function, uh, you have to define it in such a way that you can have one global minima. So assume that we are talking of a hyperspace where my w is not just 1 dimension, my w is nx dimensional. If my w is nx dimensional, then I'm talking of the space where my uh, w's and my b is included, and all those are being plotted in terms of y hat. And that hyperspace, it should have one global minima. So that is the level, the extent at which I'm talking of. I hope I have been able to illustrate with the example of 1 dimension what I'm talking about in when I say one global minima, right?
Yes, ma'am.
Okay, so I will be covering gradient descent, and maybe we will discuss the
Naive Bayes also, if possible.
yes.
Naive Bayes, is it possible for you to discuss naive Bayes?
Okay, so I will cover this in the next class, and also I would discuss the four activation functions, so that you have a more clear cut understanding of how we go about calculating the cost functions. Okay, so with this, we come to the end of this session. Maybe we will meet up next Monday then.
Yes, ma'am. Thank
Okay.
you so much for your efforts, and we appreciate your time, ma'am.